So in this video, I want to tell you the story of Plato's lost treasure. I'd always heard the rumor that back in ancient times, a shipwreck caused this treasure to be lost deep at sea, but never really believed it until I went out scuba diving one day. I stumbled across this sunken ship, and after exploring further, I came across an ancient treasure chest. When I finally got this treasure chest back to shore, I opened it and was shocked when, as though by magic, out popped the 5 Platonic solids. These 5 solids, the only ways you can combine multiple copies of a given regular polygon in a nice symmetric way, have been studied for thousands of years, and were thought by Plato to represent earth, water, fire, air, and the heavens. Anyways, as if these solids hovering in front of me weren't enough, the next thing to come out of the treasure chest was the booming voice of the ancient philosopher Plato. He told me that his treasure would only be revealed to a person smart enough to open each of the solids and then solve the question within. A solid can be opened by inputting a code onto its vertices. Each vertex starts out with a value of 0, but can be increased or decreased by 1 simply by touching a face that vertex lies on. So for example, if we start out with the tetrahedron, our tetrahedron has 4 vertices. I'll call them T, B, L, and R. As you'd probably guess, those aren't just random letters. I can orient this guy so that those represent the top, back, left, and right vertices respectively. Notice that each vertex has a number next to it, each initially set to 0. But if I touch this front face, the numbers next to the 3 vertices on that face all increase by 1. Maybe now I rotate this guy a little bit more and pick a different face to touch. Because I touch the face that L, B, and R lie on, each of their counts increase by 1. I could touch this face again if I wanted to. And we again see each of the counts increase by 1. Just for fun, I'll rotate this guy again and touch another face, but this time I touch the face in such a way that each of the vertices on that face decrease by 1. I could continue in this fashion as much as I want and rotate this tetrahedron so that I can touch any of its 4 different faces and do so to either increase or decrease the vertices on that face. Getting back to our original orientation, we see that the vertice counts have changed and are now 0, 1, 2, and 3 respectively. Plato's voice also told me that the code for the tetrahedron was 4, 9, 2, negative 3. Since there was no mention made of which vertex corresponded with which number, our tetrahedron will open if we can get the vertices to take on those 4 values regardless of where they show up. We could get there from here, but maybe for completeness, I'll reset all the vertices to their initial counts of 0. To lessen the burden of my animation, I'm going to rotate this guy just a little bit and then unfold it from a 3-dimensional object to a 2-dimensional object. I'm going to repeat that unfolding one more time, but this time I want to track where the vertices end up on our 2-dimensional unfolded tetrahedron. At this point, you could probably just start mashing buttons until you get the vertices to have the proper code, but I don't think this barbaric strategy will serve us very well when we move on to more complicated polyhedra. So maybe we should try to solve this problem a little bit more strategically. If you're a big fan of algebra, and who's not, you could label the faces and then set this up as a system of linear equations. For example, if you look at the vertex T, that's going to change anytime we press any of the faces A, B, or C. Similarly, R is going to change when we press A, D, or B. L is going to change when we press B, C, or D. And B is going to change when we press A, C, or D. At this point, we can assign the 4 digits of our tetrahedron code to the 4 vertices completely arbitrarily, and then see what happens when we solve the system of linear equations. There's lots of different ways we can solve this system. I think I'm going to row reduce an augmented matrix, which sounds more impressive than it is. If you haven't seen any linear algebra, you could solve it by substitution. It would just get really ugly and be kind of tedious. But if you're lucky enough to know some linear algebra, you can use elementary row operations to get it into row echelon form and then reduced row echelon form. What this tells me is that A equals 2, B equals 7, C equals negative 5, and D equals 0. We could check these answers by plugging them into the linear equations, or maybe it'd be more fun to actually press those faces and track what happens to the vertices. So we want to press A twice, and then press B 7 times, and then press C negatively 5 times. And then we don't have to press D at all. Sure enough, we've managed to program the correct code onto the vertices, and just like Plato promised, the tetrahedron opens up. I don't know what I was expecting to be inside the tetrahedron, but it certainly wasn't a dancing fairy asking me another question. Since trying to do a fairy voice went terribly wrong, I'm just going to tell you what she said. She told me that in order to receive the code for the next Platonic solid, I had to tell her a condition that was both necessary and sufficient for a tetrahedron code to be realizable. In other words, not all codes are even possible to put on the vertices of a tetrahedron. Which ones are and which ones aren't? Maybe we start by looking for a necessary condition. When doing so, it often helps to try to find an invariant, some aspect of the counts of the vertices that doesn't change no matter which button you press. In this case, you might notice that any face has exactly 3 vertices on it. So if we consider the sum of the counts of the vertices, which remember starts out at 0, touching any face will either increase or decrease this sum by 3. So the sum of the counts on the vertices is always a multiple of 3. Or if you want to sound really smart, the sum of the counts of the vertices modulo 3 is an invariant of the operation of pushing a face. All I'm saying is a vertex code like 1111 isn't possible because the sum of those counts is 4, and 4 is not a multiple of 3. We can prove that to ourselves by going back to our system of linear equations, putting in this code, and seeing what happens when we solve. If we again create an augmented matrix and use the same series of elementary row operations to get our matrix into reduced row echelon form, we'll eventually be able to get to a solution, but this time the solution will not contain integer values. Since we can't press a face a third of a time, this solution is not realizable, so we can never make the counts on the vertices of our tetrahedron all equal to 1, nor can we achieve any other count where the sum of the vertices is not a multiple of 3. We have a necessary condition, but is this condition sufficient? In order for a code to work, its sum must be a multiple of 3. But just because the sum of a code is a multiple of 3, does that guarantee that there's a way we can press the faces to get this code on the vertices? To see if this necessary condition is sufficient, we can go back to our series of linear equations, but rather than substitute in a code, leave constants in place of the vertex counts. For the third and final time, I'll use linear algebra to solve this system of equations, although again it can be solved in a slightly uglier fashion using more basic methods. When I finally get my matrix into reduced row echelon form, I'll have general solutions for A, B, C, and D. This allows me to take any values that I want for B, T, R, and L, in other words, any tetrahedral code that I want, and figure out what A, B, C, and D would be for that code. If A, B, C, and D are all integer values, then that code is realizable. So a sufficient condition for our code to be realizable is that these 4 expressions listed all produce integer values. Here's a brief summary of what we found using an arrow diagram. And maybe you're like, yeah, great, you have a sufficient condition and you have a necessary condition, but the fairy didn't ask for 2 separate conditions. The fairy asked for a single condition that was both necessary and sufficient. That's true, but wait. The digits of the code are B, T, R, and L. So if the sum of the code is a multiple of 3, B plus T plus R plus L is a multiple of 3. Because each of the digits of the code are themselves integers, 3 times any of the digits of the code is a multiple of 3. So 3L, for example, is a multiple of 3. Well, if B plus T plus R plus L is a multiple of 3, and 3L is a multiple of 3, the difference of those two things, B plus T plus R minus 2L, is a multiple of 3. And if I take something that's a multiple of 3 and divide by 3, I get an integer. So B plus T plus R minus 2L, all divided by 3, is an integer. The exact same logic shows that B plus T minus 2R plus L, all divided by 3 is an integer, and B minus 2T plus R plus L, all divided by 3 is an integer, and negative 2B plus T plus R plus L, all divided by 3 is an integer. What I'm saying is that our necessary condition implies our sufficient condition. So the sum of the digits of the code being a multiple of 3 is both a necessary and sufficient condition for the code being realizable, and the answer for the fairy. And while I know it's tempting to present this answer to the fairy to see what happens next, I want to hold off for just a minute because there's one more little trick I want to show you with the tetrahedron that'll end up being useful for our other platonic solids. Sometimes, instead of just looking at the effect of pressing one face, it can be useful to explore the net effect of pressing multiple faces. With the tetrahedron, since any 2 faces are adjacent and thus share 2 of their 3 vertices, if we press one face positively and one face negatively, a lot of the changes will cancel out. Let me demonstrate. Say you wanted to increase R by 1 and decrease L by 1 without changing any of the other vertex counts. All you'd have to do is find the face that R does not lie on, C in this case, and press that negatively, while also pressing the face that L does not lie on, A in this case, positively. As we were hoping, R went up 1, L went down 1, and none of the other vertex counts changed at all. Importantly, there's nothing special about R and L. We can do that for any pair of vertices. And this technique, which I'll call the +1 -1 combo, will allow us to develop an algorithm to attain any realizable code without having to mess with matrices and row reduction. I'll demonstrate by programming the tetrahedron code we were given, using a different series of steps than before. I'm going to call this algorithm the Rubik's Cube algorithm, because even though I don't really know much about solving a Rubik's Cube, I think the idea is to kind of start out by getting one part, and then figure out a way to get the next part without messing up that first part, which is basically what our algorithm is going to do. Because our +1 -1 combo doesn't change the overall sum of the counts on the vertices, we want to start out by pressing any face at all enough times to make the sum of the counts on the vertices equal to the sum of the code. So 4 + 9 + 2 + -3 is 12. So we pick any face we want. I'll pick D arbitrarily and press it 4 times to make the sum of the vertex counters equal to 12. Now that the vertex sum matches the code sum, we're done with step 1 in our algorithm and can move on to step 2. In step 2, you use the +1 -1 combo to set the first digit of the code while changing the second digit of the code. We want to increase t from 0 to 4, which means we'll be decreasing r. As we saw with the +1 -1 combo, to increase t and decrease r, we touch the face that does not contain t negatively and touch the face that does not contain r positively. To get t from 0 to 4, we perform this combo 4 times. Now that t is set correctly, we're done with step 2 and move on to step 3 of our algorithm. Our goal here is to set r to its correct value by changing L. The relevant faces are those not containing r and not containing L, so C and A respectively. And since we want to increase r, we'll be decreasing face C, the one that r does not lie upon. Now that r is set to its correct value, we're done with step 3 of our algorithm and move on to step 4. Step 4 is much like the previous 2 steps, except now we want to pick faces to change L and B. Our goal being to increase L from -5 up to +2. We've set L to its correct value, so we're done with step 4. You might notice that B is already set to its correct value, and that's not a coincidence. Because in step 1 we made sure that the sum of the code was set to its correct value, the fact that the +1 -1 combo doesn't change the sum of the vertices guarantees that the Rubik's Cube algorithm will produce the correct code once we set 3 of the 4 digits correctly. We didn't get lucky. This algorithm will always produce the correct code anytime the sum of the digits of the code is a multiple of 3. In fact, the existence of this algorithm is enough to show that the sum of the digits of the code being a multiple of 3 is not only a necessary condition, but also a sufficient condition. The algorithm replaces that quasi-proof I did in orange earlier. At any rate, we're finally ready to share our findings with the fairy. We excitedly tell her that a necessary and sufficient condition for a code being realizable on the vertices of our tetrahedron is simply that the sum of the code is a multiple of 3. She's very impressed with our finding, but there's no treasure yet. All this does is get us past level 1. In the next video, we'll conquer levels 2, 3, and 4, which are analogous to level 1, but involve different platonic solids. The challenge question that I'm going to leave you with will be the one that'll get us started on level 2 in the next video. And what it asks is this. If we orient an octahedron so there are vertices facing up, down, left, right, front, and back, and we have the same rules as before, where each face of this solid is a button that can either increase or decrease all of the vertices on that face by 1, and the vertices are all initially set to 0, how would we press the faces in order to achieve the code shown in front of you? If you figure this out and you're especially ambitious, you can try to find necessary and sufficient conditions for a code to be realizable on the octahedron. And if that's not enough, then move on to the cube and the icosahedron. And if you get stuck anywhere, don't worry about it. I'm going to work out all these solutions in next week's video. However, in the meantime, if you want to share any thoughts, questions, or solutions in the comments, I'll check them out.